Volume by cross-section method. In this video, we use definite integrals to find volumes of three-dimensional solids. Thanks in advance for watching this video. If you liked this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. We should first define just what a solid of revolution is. A solid of revolution is a three-dimensional object obtained when a region in the plane is revolved around a line in the same plane. The resulting object is known as a solid of revolution. The volume of this solid may be calculated using integration. We start by studying the volume by integration of a cross-section. We start with some arbitrary region bounded by the function f of x from x equals a to x equals b. We now rotate this area around the x-axis by a complete revolution. The curve will map out the surface of a solid as it rotates. This is called a solid of revolution, as depicted in the diagram. We can approximate its volume by cutting it into n thin slices. When we slice a solid, we get cross-sections of the solid. We can divide the interval into k sub-intervals as follows. If each slice has cross-sectional area A of x and thickness delta x at each particular x value, then the volume of the slice is its area times its thickness. Adding up the volumes of the slice, we have approximately the total volume of the solid, and we recognize that this is a Riemann sum. If n is very large, then delta x is very small, and the slices are very thin. So we can define the volume of the solid as the limit of these sums as n approaches infinite. But we recognize the limit of Riemann sums as a definite integral, and so we have the following definition. Let A of x be the area of the vertical cross-section at thickness x of a solid body extending from x equals a to x equals b. Then its volume is. The volume of the solid is equal to the integral of its cross-sectional area. Similarly, the volume of the solid formed by revolving the region bounded by the curve in the y-axis between y equals c and y equals d around the y-axis is given by. We now apply the slicing method to derive a formula for the volume of a pyramid whose base is a square of sides L and whose height is h. Find the volume of the square-based pyramid. In order to find volumes, we need to identify three things. The base region graph shows the length of a side of the cross-section shape and the limits of integration. Consider the pyramid shown in figure below. We place the origin at the vertex of the pyramid and the x-axis along its central axis. We first want to determine the shape of a cross-section of the pyramid. We know the base is a square, so the cross-sections are squares as well. We now determine a formula for the area of the cross-section to use in the integrand. We can express the area of the cross-section as a function of x by observing the similar shapes. Thus, the cross-sectional area is a function of x is given as follows. Integrate the area formula over the appropriate interval to get the volume. Then we find the volume of the pyramid by integrating from 0 to h. The volume of a pyramid is 1/3 the area of the base times the height. Find the volume of a pyramid of height h whose base is an equilateral triangle of side L. Consider the pyramid shown in figure below. We place the origin at the vertex of the pyramid and the x-axis along its central axis. We first want to determine the shape of a cross-section of the pyramid. We know the base is an equilateral triangle, so the cross-sections are equilateral triangles as well. We can express the area of the cross-section as a function of x by observing the similar shapes. The area of the equilateral triangle is square root of 3/4 times of square of the side length. We now perform the calculations. Find the formula for the volume of a right circular cone of height h whose base is a circle of radius r. To find the volume of the cone, we place the origin at the vertex of the cone and the x-axis along its central axis. We know the base is a circle of radius r, so the cross-sections are circles as well. We can express the area of the cross-section as a function of x by observing similar shapes. The area of the circle is pi times radius squared. We now perform the calculations. Find the volume of a sphere of radius r. We place the sphere so that its center is at the origin. Then the vertical cross-section of the sphere at x is a circle whose radius r satisfies the Pythagorean theorem. So the cross-sectional area is given by. We now perform the calculations. The base of a solid is a square, one of whose sides is the interval from 0 to L along the x-axis. The cross-sections perpendicular to the x-axis are rectangles of height y equals x squared. Find the volume of this solid. For each x, the rectangular cross-section has base L and height x squared. The cross-sectional area is then base times x squared. And the volume of the solid is given as follows.